Recording is rolling. It is Thursday, December 5th. So you guys have your energy quizzes back in your return folders. If you missed any questions, want partial credit back, then just write out the solutions and turn it in. I'll give you partial credit back. Reminder, we're doing a optional show and tell Friday, 8 days from now. You don't have to do this. It's not for class credit. But if you wanted to bring anything to school and share with classmates, you could. Or if you email me a picture, I could put it into a PowerPoint and then you could present it that way. So up to you. You guys know there's an in-class quiz coming up on Tuesday. It's going to be on both energy and momentum, so 10 questions for each. This will be a little bit easier than the questions I usually send you guys home with the take-home quiz, because these are pretty fundamental, basic. In fact, some of the Kahoot questions you guys see today, I bet are going to show up on the momentum half of this. Right? So maybe those type questions. Right? Right. Maybe a few basic equation type questions, but nothing too crazy, I think. Right. And then we'll start the midterm review this upcoming Wednesday. That'll take us a few days, and you guys will be all ready for this midterm. Right. So here's today. We're doing Kahoot, momentum, and then about the last 10 minutes of class or so, I'll walk you guys through. Oh, where do I have one of these ballistic pendulum questions? You guys remember seeing this? So I'll walk you guys through in principle what this is about, but we'll do a numerical example. So I'll throw some numbers on the board. All right. And that is the plan. All right, so over here. Oh, I didn't do that. All right, you guys are all ready. All right, pens on the board if you need that. All right, momentum of an object defined as mass times velocity, right? P equals mv, right? Mass times velocity. Here, let me find the poster for that that one. So is that's just that right there, right? Mass times velocity. Okay. Now remember, because this is a vector value, if somebody guys, if someone's moving to the right or moving to the left, is that different momentum? Yeah, that could be positive versus negative momentum. So keep that in mind. That might show up later this Kahoot. All right, points on the board. All right. If the momentum of an object changes, then what? Uh, yeah, all those would be true. So momentum is changing, so mass times velocity would be changing. If mass is the same, then the velocity is changing. Hang on, if the velocity is changing, then it would be accelerating, and what causes an acceleration is a force. So actually, if any one of these are true, then they're all true because they all go hand in hand. Okay. So that could be, we're talking about impulse, right? Impulse, right? While we're on this question, let me give you guys a sort of a weird kind of example of this. Maybe a counterexample. What if the mass does change? Now, in this class, we're not normally dealing with that, but I want to stretch your guys' imagination a little bit. What if you have a conveyor belt? Like a conveyor belt. Okay. And maybe I got a bunch of bottles on this conveyor belt. Bottle, bottle, bottle. Okay. And as the conveyor belt's going along, maybe it's like some factory, we're filling up these bottles. So here's like they were filling up with water, like fill up with water. Okay. And this whole conveyor belt's moving this way. Okay. Maybe it's moving to the right with a constant velocity. Guys, would it require a force? Would it require a force to keep this going at a constant velocity? Okay. Yes, because the mass is changing. You guys see every time you fill up one of these bottles, you're changing the mass, right? So that's sort of a little bit manipulated version of this. Instead of the delta V, I could leave the V the same. I could move the delta over to M, like a change in mass. Ooh, do you guys see that? Okay, so just to stretch your guys' imagination a little bit on that one. I don't think that's going to show up on the midterm or anything, though. All right, we got Ian, Zach, I'll call you Tommy Two-Tone here, Olivia, Hunter. Table tennis ball launcher is fired. Compared to the force on the ball, the force on the launcher is. Yeah, the same. Hey, is that a law of motion? Which law of motion is that? Newton's third law. Yeah, equal and opposite forces. Right? Sometimes they'll say a cannon and a cannonball. Same idea, right? Right? There's just some blast that happens inside the barrel, pushes everything equally. Yeah, same equal and opposite forces. Same force. Got Elise, Luciana, Isabel, Ian, Olivia. Table tennis ball launcher is fired. Compared to the impulse on the ball, the impulse on the launcher. And also the same, right? So remember, you have two perspectives on impulse. So I know it's the change of momentum. That could be mass times change of velocity, right? That's provided by a force acting for some time interval. That's the other perspective, right? And we just said from the last question, it's the same force, opposite directions, same magnitude force, right? And for the same time. So if it's the same force for the same time, that's the same impulse on the ball as back on the launcher, opposite directions. Okay. Maybe there's zero momentum ever in the system, but positive and negative, right? Cancels out. All right. Yeah, Isabel, Zach, Olivia, Luciana, Ian. A collision is considered elastic if. Ooh, nice, nice. All right. So in class, I've really been emphasizing this gold one. The kinetic energy is conserved, right? But that does go hand in hand with some of these other ones. Like I know if they stick together, that would have been inelastic. Right? If they bounce off each other perfectly, that's elastic. Okay, so the blue one is probably a pretty good answer also. Right. If there's ever a collision, there's lasting deformation. Do you guys think that some of the energy would have gone into deforming, like force times distance? Right. Right. At the end of class today, we're going to do you fire a bullet into a block of wood. I bet that bullet like pushes the wood fibers out of the way, but there's some energy that goes that way, which would make it an inelastic collision. Okay. All right. Yeah. So all those could be signs of elastic. All right. Elise, Zach, Olivia, Luciana, Ian. Suppose standing on a pond, there's no friction between your feet and the ice. Sounds like the magic school bus. How do you get off the ice? Yeah, have to throw something the opposite way. Throw something the opposite way. Right. So you guys remember this clip right here? Right. So on this frictionless baseball field, look, you guys see once they're in motion, they're just sliding, right? And they can't really stop what they're doing. So you need this crane to put them all in place, right? And now once it fixes them in place, they're just kind of stuck there, right? Until er, until you throw something. Throw it, throw it. Oh, whoa. All right, and now you're moving the opposite way. Right. With so equal and opposite force, push you back the other way. All right. That's that right there. That's how you get off the ice. Elise, Zach, Luciana, Olivia, Ian. Freight train rolls along a track with considerable momentum. If it were to roll with the same speed but had twice the mass its momentum would be. Should be twice as much. Yeah. So momentum is mass times velocity. So if it's twice the mass, it should be twice the momentum. All right. All right. Are you guys okay with why it'd be double? All right. So momentum is mass times velocity. Sorry, I think I skipped through that a little fast. Just trying to get this order. Right. Momentum is mass times velocity. If you double the mass, that doubles the overall momentum. Right. That's all. All right. Yeah. Got Jonathan. Ooh, Tommy Tutone is back. Ian, Elise, Zach. Cannon recoils from launching a cannonball. The speed of the cannon's recoil is small because Yeah, the cannon has so much mass compared to the cannonball. Yeah. All right. So here, I do want to draw this one out a bit. Okay. So actually, you know what? I think I do have a poster for this one. I just remembered. Here it is. Here it is. Right. So this could be a skater and a ball, but hey, could this be like a cannon and a cannonball? You just replace this guy with a cannon. Same idea, right? So if they start out at rest, there's zero momentum in the system. Then fire, pow, or throw the ball. Either way, you get mass velocity of the ball, mass velocity of the cannon. Right, go opposite ways. Subtract this over. Right, so they have equal and opposite momentum. Right. Okay, and then the smaller mass is moving really fast, and the larger mass is moving really slow. That's all. Wow. Luciana, Jonathan, Tommy Two-Tone, Elise, Ian. In order to catch a ball, baseball player moves his hand backward in direction of the ball's motion. Doing this reduces the force of impact on the hand because uh should be that you're extending the time interval of that collision, right? Now, why is it not the blue one? Because if that ball's coming in, has some mass and some velocity, and you bring it to a stop, the change in momentum of the ball, which is the impulse, is the same regardless of how you stop it. Here, I'll give you guys a picture here. I'm gonna put up some notes from earlier today. So here's the guy's gloved hand right here. Here comes the ball. Right. No, a baseball is more like a sixth of a kilogram. I'll just call it 1 kilogram just to make the numbers easy. Suppose it's coming in at like 10 meters per second. Right? Is that? So it has 10 units of momentum, and you bring it to a stop. Because if you bring it to a stop, what's the impulse of bringing it to a stop? 10 kilogram meter per second, right? Because mass times velocity, right? Mass times change of velocity, right? Or you can say negative, but whatever. Right. Now, if you bring it to a stop in 1 second or 5 seconds, it doesn't matter. The impulse is the same because it's going from this speed to zero either way. Right. But you guys have a different perspective on impulse also. Now, impulse is mass times change of velocity, but it's also a force over some time interval, right? Right. Let's look at different time intervals. As let's say you bring it to a stop in 1 second. How much force does that take while you're stopping it? 1 times what is equal to 10? 10 takes 10 newtons. 10 newtons for 1 second gives you 10 newton seconds or 10 kilogram meter per second, right? What if you extend that time to twice as long, like 2 seconds? How much force is that? Huh? 2 times what is 10? 5 newtons, right? 5 newtons times 2 seconds, that would be the same impulse, right? Okay, so by doubling the time, that's half the force. You see that? Right? You guys ever drive on the interstate? You see like a big concrete barrier and there's an attenuator in front of it? Right? So here's a big concrete barrier right here. Right? Here's one of those attenuators. So that, especially you're either getting sleepy or reading your text and get distracted. You're like, oh, wait, I'm driving on the interstate. You crash into this concrete barrier. Well, if you come to a dead stop, pow, that's stopping the car really fast. That's a huge force. But if you run into this attenuator, it slows down that stopping time. Now it's instead of like a tiny fraction of a second, maybe it's like like 1 second or 2 seconds. Right? You extend the time interval, therefore you decrease the force during that collision. Okay? All right. How about this? You're in a burning building, and you're on the 3rd story. So 3rd floor window. Right. So you're up here in a burning building. Right. You're up here, way up here, and you look down, and you see the sidewalk below. And the only way out is you gotta jump. Right. And then you say, wait a minute. If I go over to this window, I see a nice trampoline right here. Right. Guys, do you want to jump and land on the sidewalk or jump and boing, land on the trampoline? Trampoline. Right. Now, either way, when you get down to here versus here, let's say you and your friend made opposite decisions. Somebody chose poorly. You're going to find out. Are you and your friend falling at the same speed at this point? Yeah, and let's say you have the same mass, same speed. That's like the same momentum. And you're going to come to a stop. That's the same impulse. But here, the time interval is boing is extended. That's more time to come to a stop. That's less force. Ooh, that's less force. That sounds better. Yeah, I'm gonna jump on the trampoline. All right, Jonathan, Tommy Two-Tone, Elise, Zach, Ian, Zach. Car traveling along the highway needs a certain amount of force to stop. More stopping force could be required when the car has. Yeah, there you go. So more mass, harder to stop the car, more momentum. That's mass times velocity, harder to stop the car. Right. Also, if you stop the car in a shorter distance, that's also more force. We just kind of talked about that with the attenuator, right? Right. Does that make sense? All those? All right. All right. So force that could be mass times change of velocity divided by the stopping time. Right. It looks a lot like Newton's second law of motion. M times delta V over delta T. That looks like F equals ma. Right. Hunter, Jonathan, Elise, Tommy Two-Tone, Zach. The force of an apple hitting the ground depends on. There you go, all the above. Right. So isn't it true that the faster the apple is falling, the more force it takes to bring it to stop? So if it falls from a tall tree rather than the short tree, I think that's more force. Right. How about the time of impact? Ooh, that's kind of what we were just thinking. If the apple hits, say, a concrete ground versus a trampoline, or if it hits a hard ground versus mud, or something like that. Now, how about if the apple bounces or not? I wonder which is more force. If it lands in the mud and goes inelastic, or if it goes boing and rebounds from the ground. Which one is do you think guys think is more force? Huh. Let's try this out. Okay. So got got tree, got one branch and one apple. Ground. Right, this is some height it's falling from. And when it gets right about here, right, now this apple is falling really fast. It's got some mass. It's got some velocity. Okay. Okay. And then maybe it hits the mud and it goes and sticks in the mud like inelastic collision. It comes to stop. Right. Here, let's put some numbers on here. Let's call the mass 1 kilogram. So equals 1 kg. Right. Let's say it's falling at like 10 meters per second. Okay. And then it comes to a stop. That's 0 meters per second. Because what's the impulse just delivered to that apple? 10 kilogram meter per second or 10 Newton seconds, right? So like 10 units, right? What if that apple bounces? Boing. I kind of drew that bad. Right here. Redraw this a little bit. I should have left some space to bounce this apple. All right, apple. Right. Now let's say it bounces. Boing. So it was hitting the ground at 10 meters per second, and then it rebounds, let's say like straight up at 5 meter per second. So let's say one dimension. So it comes down at 10 meters per second, rebounds boing at 5 meters per second. Because what's the change in velocity of that apple? What's the difference between -5 and +10? 15? Can I do it on a number line? If -5 is here and 10 is here, you guys see the difference would be like 15, right? And if the apple has a mass of 1 kilogram, is the impulse 15 units? All right, so when the apple stuck in the mud, the impulse was 10 Newton seconds. When it bounces, boing, the impulse is 15 Newton seconds. You guys see that? Right? Okay. Now, assuming those collisions are the same time interval, just to keep that the same, apples to apples. Okay. Which would be more force? Sticking in the mud or bouncing off the ground? Which is more force? Show of hands. How many of you guys think sticking in the ground is more force with the 10 Newton seconds? How many of you think bouncing off the ground with 15 units? Yeah, that's right. Yeah, this is definitely more impulse. So for the same time interval, that would be more force, wouldn't it? Be more force bouncing, right? Oh, you know what that kind of reminds me of too? Do I have it down here somewhere? Where? I think it's going to show up later anyway. Right. This is kind of what we were just talking about. Here's sticking in the mud. Here's bouncing off the ground. But boing. That's kind of like inelastic versus elastic, isn't it? Right. Guess what? I think that question's going to show up fairly soon. So let's see. We got Luciana, Alexander, Hunter, Tommy Two-Tone, Zach. Moving freight car runs into an identical car, same mass, that had been at rest on the track. The cars coupled together. Sounds like inelastic. I think you guys did a lab on that. Compared to the velocity of the first car before the collision, the velocity of the combined car after the collision. Yeah, half as much. Half as much. Right. So why half as much? Do you guys see this is an inelastic collision? Right. Inelastic collision. Right. Right. So actually, if one car started at rest, then this V doesn't exist. If they're the same mass, then you could call this M and M. Okay. That could be like this. I got this from earlier today, so let's just do this. Right. Let's say 1,000 kilograms and 1,000 kilograms. You guys see that? Right. Now let's have this one start at rest that's 0 meters per second. I'll get this cart rolling. Let's call it 12 meters per second, just to throw a number at it. Okay. And then they collide. They stick together, and now they're moving together. Well, how fast? So here's my principle: is momentum is conserved. That's conservation of momentum. I'll call this an inelastic collision. Let's say perfectly inelastic. So all the momentum was provided by this cart in motion. The other one had 0 to start with, so you can say plus 0 or just ignore it. Either way. Then they stick together, make m plus m. That's like 2m, moving at some common final velocity. Let's throw some numbers in here. So I got 1,000 kilograms at 12 meters per second. Then after they collide, now that makes 2,000 kilograms, moving how fast? Can you guys solve how fast? How fast is that? 6. Aha! It have to be 6 meters per second. You guys see 6? Right? Is that? Luciana, Alexander, Hunter, Tommy Two-Tone, Zach. Piece of putty moving with 2 units of momentum strikes and sticks to a heavy bowling ball, initially at rest. After the putty sticks to the ball, both are set into motion with the combined momentum of. Ooh, 2 units, 2 units. Such as conservation of momentum. It says putty, I drew a bullet. Same idea because it's inelastic, it sticks to it. Either way. Okay. So if it comes in with MV of 2 units, yeah, then they both roll off together with 2 units of momentum. That's all. Right? Right. Oh, you know what question I think is coming up next is probably this one down here. Suppose the next question talks about a bouncy ball coming in with 2 units of momentum, and it boing bounces off with 1 unit of momentum the opposite direction. What does that send the bowling ball doing? Let's see if you guys get this next question. A bouncy ball coming in with 2 units of momentum. Strikes and boing, bounces off the heavy bowling ball. After the bounce, the bowling ball is set into motion with the momentum of. More than 2 units. More than two. More than two. Let's go back and take another look at this. So say this mass is like 1 kilogram and this is 2 meters per second. So 1 times 2, that's 2 units of momentum. Then it boing bounces the other way. Let's say it's going 1 meter per second the other way. Guys, what's the difference between 2 to the right and 1 to the left? 2 to the right, 1 to the left. The difference is 3 units. isn't that, and then if that's mass times velocity, isn't that how much momentum was transferred into the bowling ball? That was the impulse on the bowling ball, right? So, okay, you guys get that? Okay. So this bowling ball is rolling off with 3 units of momentum to the right. Guys, which bowling ball is rolling faster? The one on the top or the one on the bottom? The one on the bottom. Ah, this guy's rolling faster. With the elastic collision, it's going to roll faster. Okay. More impulse was transferred into that bowling ball. All right, Elise, Zach, Hunter, Alexander, Tommy Two-Tone. Force that accelerates a rocket into space is exerted on the rocket by the exhaust gases. So the rocket pushes on the gases push on the rocket. Guys, which force is bigger? The force on the gases or the force on the rocket? Which force is bigger? Huh? Show hands. How many guys say it's the same force? Who says the same force? Who remembers Newton's third law of motion? What's Newton's third law of motion? Equal and opposite forces. Yeah, guys, it's the same force. There's a force back on the gases. There's a force forward on the rocket. And it's the same force. Okay. How about this? Suppose you're taking a trip to Mars. So we're halfway from Earth to Mars. Like, oh, dang it, I forgot my cell phone. Let's go back to Earth. And you got to make an about face and go back to Earth. All right, guys, how do you turn around in space? Do you have to blast some gas somehow? Right? And does that gas just go flying off into space forever? Yeah, and it's you blast it opposite of the way that you're trying to go. Yeah. It's the same force both ways. In fact, the rocket's pretty heavy. That gas is pretty light, so you have to blast a lot of gas. Elise, Hunter, Alexander, Zach, Tommy Two-Tone. Cannonball shot from a long barrel cannon travels faster than one from a short barrel cannon because that cannonball would receive a greater. Yeah, impulse. Right? No, all else equal. Yeah, maybe it's the same chemical reaction with the same amount of gunpowder. It could be the same force. But if you have a long barrel, you're extending that force over a longer distance and a longer time interval. Ah, so force times a longer time interval, that'll get you going faster. Yeah, that's why you see artillery have like really long barrels, or like why does a rifle have a really long barrel compared to like a little pistol? Yeah, because that force can be extended over a longer time, get it going faster. Yeah. Elise, Zach, Tommy Two-Tone, Hunter, Alexander. 2 kilograms, 3 meters per second. What's the momentum? 6 kilogram meter per second. So mass times velocity, right? 2 times 3 is 6. 4 kilogram ball has 20 kilogram meter per second of momentum. What's the ball's speed? Aha. So 4 times 5 is 20, right? 4 times 5 is 20. 4 times 5 is 20. Ball's moving 6 meters per second, has momentum 24 kilogram meter per second. What's the ball's mass? 4 times 6 is 24. You guys got 4 times 6 is 24? All right. Where are we sitting here? Got Hunter, Tommy Two-Tone, Elise, Alexander, Zach. While roller skating, Granny collides with her tiny grandson Ambrose, who had been at rest, ignoring any friction. Ambrose's speed after the collision will be greatest when. Bouncing collision. Bouncing. Because that's more elastic. Isn't that just this right here? All right. Here's Granny. Here's Ambrose. If they collide and stick together, maybe it's still fast together. But if this is Granny and this is Ambrose, boing, it flies off Ambrose. Now he's going really fast. Hunter, Tommy Two-Tone, Elise, Alexander, Zach. Yeah, oh, here's for the win. You guys ready for the win? For the win. If all people, animals, trains, and trucks all over the world began to walk or run towards the east. Yeah, you guys know the Earth is already spinning eastward, right? So the Earth is already spinning towards the east. What if everybody on the surface started to walk towards the east? Ooh, two winners. A bit slower. A bit slower. Let's look at why. Ooh. All right. So here's the Earth. North Pole, South Pole, equator, and oh, it's already spinning towards the east, right? You guys see they're spinning towards the east, spinning this way. Zoom, 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 zoom. Right. Now, if everybody on the surface, guys, if everybody on the surface starts to walk towards the east, are you sort of pushing the ground beneath you back towards the west? That's one way to think of it. That's in terms of forces. In terms of momentum, this is actually more of an angular momentum type question. Right? So the Earth and everything on it has some angular momentum, right? Spinning eastward. If you separate out everything on the surface from the ground beneath, and everything on the surface is going even faster towards the east, then the resulting Earth beneath it is again kicked back towards the west a little bit, so it slows down a little bit. Right? I don't know if you'd even be able to measure that because it'd be such a tiny effect, but unless maybe you had like a little tiny asteroid, you had some pretty big astronauts walking around, maybe you could notice that a little bit or something. But it's physics principle, right? All right, you guys good with all that? All right, let's see who won. Who won the Kahoot? With the bronze, Alexander. The silver, Zach. And the gold, Elise. All right, nice job. Nice job. All right, you guys good with those Kahoot question? All right, so there's one more thing I want to do with you guys today, which is let's solve one of these ballistic pendulums. There it is, ballistic pendulum. Okay. All right, so here, the first let's walk through this. Oh, you know what? I almost forgot. I do have a video on this. Here, let's run the video so you guys can see the animation. Check out this animation. Okay, so guys, here's what happens. We're gonna fire a bullet into a block. It's going to collide inelastically because it embeds, and then the block on the pendulum swings up to, well, hey, look, is that a protractor right there? Like some number of degrees, right? Let's do that version too. I'm going to give you guys an angle and the whole thing. All right. So we'll do it. Oh, now there's different ways you can go with this question. I've seen different variations, but the classic question is, what's the firing speed of the bullet? And if you know, here, guys, everybody got paper out for notes? We're going to try this out. If you know the mass of the bullet, the mass of the block, and how high it swings up to, then there's enough information where you can solve this. Okay? So let's try this out. Okay. So I'll call this ballistic pendulum. Ballistic pendulum. I got some block with some mass here. I got some bullet, has some mass and say some firing speed. Has the bullet, right? And ultimately, that's what we want to know. So that's the last thing we're going to find. But maybe I'll give you numbers on all these other things. Okay? And when it embeds in the block, the whole thing is going to swing up to some angle. and there's going to be a height change. Here's the bullet inside the block, embedded like that. Okay. And there's variations on this. So I've seen a variation where like the bullet goes through the block. I've seen a variation where they tell you the firing speed of the bullet and how high does it go. But we got this. All right, so I need to give you some numbers. Let's say the mass of the bullet is like 0.010 kilograms, right? Which is like 10 grams. You guys see this little 10-gram guy right here? Your smallest lab weight. So this is basically the bullet. Your smallest lab weight is the bullet. Okay. Let's call the mass of the block 1 kilogram exactly. Right. Let's say instead of telling you the height change, I'm going to give you the length of the pendulum and the angle. So let's say the length of the pendulum is like 1.5 meters. And let's say this angle is like, 23 degrees. Okay. Okay. All right. Now there's enough information that you can solve this. I'm gonna do all my math over here. I think I'll be able to fit this all on one page. All right. So there's the setup. All right. So while you guys are copying that down, just to review what we got. Okay. We got some bullet fired into a block and it swings up to some height. Okay. Now, I really want to know what's the firing speed of the bullet. And this is maybe it's 1870 and we got the new revolver. Pew, pew, and how do we figure out how fast this can fire? And we're going to use this method right here. Okay. So we get the mass of the bullet, which is like 0.010 kilograms. So that's 10 grams. That's this guy right here, but I put it in kilograms. Better for the math. Okay. The block, I'll just call 1 kilogram. So maybe like this is your block right here. I got a 1.5 meter long pendulum. So that's about human height. And it swings up to, 23 degrees. So if you had a protractor, just like the animation, you saw a protractor embedded. Okay. All right. So I'm thinking I can split this into maybe like 3 parts. So there's a little bit of complexity. It's like a multi-part question. Okay. Guys, what's one thing I got to do to solve this? What's one thing? Height change. Yeah. Right. So we got to do some geometry. Figure out, well, what is this height change right here? Well, it's h. Now that, who remembers, how do you get the height change? Do you guys remember how to do that? You guys remember this right here? Right. So you guys did a lab like this. You're trying to figure out what's the speed at the bottom for a pendulum. You guys measured it with a speed gate, but you also calculated, so, yeah, look, it's about the same thing. Right. So let's go through this again. Is this length and this length, is that same length? Yeah, it's the same length. So the string length is like fixed in place. Do you guys see a nice right triangle right here? Nice right triangle. And is this leg here of this right triangle just L cosine theta? Playing off this theta, that L cosine theta right there. Right? And then if you want this height change right here, that's just the difference between the full L and the L cosine theta. So I'll call it L minus L cosine theta. Then if you want to, you could factor out the L and it looks like that. Right? L times 1 minus cosine theta. Okay, you guys got that? All right, so I'm gonna take this and use that for my geometry. I'm gonna say the height change is equal to L times 1 minus cosine theta. That's 1.5 meters times 1 minus cosine of 23 degrees. Let's see what that is. That's 0.119 meters. Okay. All right, so that's one part, right? How to figure out what's the height change. Got it right there. Okay. Now, if you know that height change, actually, that's kind of the last thing that happened. So chronologically, there was a collision first. Guys, collision. Does the collision sound like energy or momentum? Momentum. And then there was a height change. Does that sound like energy or momentum? That's energy. Ooh, and we just found the height change. So actually, we're going to solve this backwards in time. We'll start with the height change and then calculate, okay, well, what collision would have set it going so fast, blah, 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 right? So height change. Okay, so when the block is at the very end, it has all what type of energy? Potential energy. So I'm setting this up. I'm setting up sum of energy at the bottom equals sum of energy at the top. And at the top, it's all potential. And what's the formula for potential energy? MGH. Right. Oh, actually, sorry, it's man. Okay. Let's do this. Let's do m plus m times gh. Okay, because it's the block plus the bullet. Okay. And what kind of energy at the bottom? Is kinetic down here, right? So kinetic turns into potential. Okay. And what's the formula for kinetic energy? 1/2 mv squared. Now I'm going to consider the block plus bullet all together. So 1/2 mv squared like that. Is that? Now, if you forgot to include both the block and the bullet, like I almost did right here, that's still okay either way because all the mass stuff just cancels out anyway, right? Right. That's a really common thing to happen back in the energy chapter, right? And I really want to know how fast was this bullet plus block together moving at the bottom to send it up to that height. Right? That's this V right here. That's not the firing speed of the bullet, but that's a middle step that'll eventually let us figure out that later on. Okay. Right. And oh, look at this. If you cross multiply 2 and take the square root, isn't that speed just square root 2gh? Hey, isn't that keep showing up over and over and over in this class? Square root 2gh. Right? However fast it's going down at the bottom, and how far high it ends up going, that's the relationship. V square root 2gh. Okay. That's the post-collision speed. Okay. So I think we can solve this right here. Square root 2, I got 9.8 meters per second squared. I got a height change. Well, we already took care of that. We did the geometry. We got 0.119 meters right there. All right, let's put that all together. So square root 2gh. I'm getting this many meters per second. Okay. Again, that's not the firing speed of the bullet yet. That's how fast was the block with the bullet in it swinging at the bottom so that it swings up to that height. So we're about halfway finished here. Okay. But how did the block get that speed? Well, because the bullet crashed into it. So what's my next setup right here? I have to do conservation of what? Momentum. Sum of momentum before the collision equals sum of momentum after the collision. Okay. And before the collision, leading up to the collision, all the momentum was provided by which object? The bullet. Yeah. So mass of the bullet times the firing speed of the bullet. Oh, that's what we were actually solving for. There we go. So what we're trying to find now it just showed up for the first time in the equations. Right? Right. This collision happens right here. Bam. Is this elastic or inelastic? Inelastic, because it sticks to it. It sticks into it. So I'm going to say mass of the block plus the bullet together times the post-collision speed. Okay, so that. See if you guys are following. What is this post-collision speed right here? What is this V? What number goes into it? 1.527 meters per second. That goes right there. That's what we did all this energy stuff for, was to figure out after the collision how fast were they going. Okay, does that make sense? All right, and then let's put some numbers in here then. So mass of the bullet 0.010 kilograms times V bullet, which we're solving for, results in, well, I'll go ahead and combine these masses because I got 1 kilogram from the block plus 0.01 kilograms from the bullet, so all together. And they're moving together now at 1.527 meters per second. Right, guess that? So the last step, all I gotta do is divide down the mass of the bullet, and I got the answer. Mistake. The mass of both combined times the speed they're moving together divided by the mass of the bullet. That tells me the firing speed of the bullet. To look at that, about that number right there. All right. So we solved this backwards in time. We started with the last thing that happened and went reverse chronological to get to the first thing that happened was the bullet was fired at the speed. Right. So what if we walk through chronologically what happened? Right. And that's just this whole math backwards. So the bullet was fired this fast. It has this mass and this speed, so it embeds in the block. So inelastic collision, and it ends up having to move this fast as a result. Right, the 1.527 meters per second, the block and bullet together. that speed is going to translate into some height change. How high? Well, speed is square root 2gh. So that height change ends up being 0.119 meters. And how we figure out that 0.119 meters, so that came from the geometry of a pendulum swinging. That's L times 1 minus cosine theta. And I gave you the L and I gave you the theta. Okay, so that's the whole thing backwards. Okay. Okay, I'll go through this one more time because we're seeing a few times to try and digest this, right? Now let's go through the way we actually solved it. So I gave you each mass, I gave you the length of the pendulum and this angle. Right? Okay, so first thing we did was we solved some geometry right here. Solve some geometry. So well, if I know this L and this theta, I can do this geometry and solve for this height change. And I know I'm going to need this height change. So this is a little bit shy of 12 centimeters right here, right? Actually, I got it right here. You guys see this ruler right here? Here's 11.9 centimeters right here. Bam. That is the height change you're looking at right there. Okay? 11.9 centimeters. I put it in meters, of course. Okay. Then I said, well, if you do conservation of energy, you can figure out how fast this was swinging at the bottom to reach that height. So that's conservation of energy. The mass cancels. And speed is square root 2gh. So you plug in g, you plug in this h right here, and you get the speed of the block and bullet together moving at the bottom. Then you say, well, how did it get that speed? Well, it got that speed from this collision, and that's conservation of momentum. So mass times velocity of the bullet was providing all the momentum. We're solving for that velocity. Okay. And it gets the block and bullet together moving at this velocity we just found from energy. So you plug that in. And the last step is divide by the mass of the bullet, and you get what had to have been the firing speed of the bullet. Okay. Here's the whole thing. Forwards, backwards, and forwards. All right, and that is a wrap on today.